let's welcome on stage our next speaker. It's Sam Bellen. He is from Belgium. And it's another security talk today. Sam works with Auth0, where he makes authentication and identification as easy as possible, while still keeping it secure. So I think Sam just came today from another conference, right?
I did, yeah.
Are you happy you're home?
I'm not home yet because I live on the other side of the country. I live in Hasselt, so that's still a 2-hour train ride.
Oh.
But I'm happy to be back in Belgium, yeah.
Okay, so please go on. We can give an applause, right? I forgot.
Thank you so much for joining me in this Friday afternoon. I know it's close to beer o'clock, but I will have to go through 30 minutes of some heavy material for you. Who has any clue what HOSE means or what it stands for? One hand. Cool, hopefully you'll learn a thing or two, because I will try to explain what HOSE is by the end of this talk, but I'll give you a spoiler right now. It stands for JSON Object Signing and Encryption. Who of you has used JSON Web Tokens before? More hands, cool. JSON Web Tokens are part of a bigger specification, which is the HOSE specification, which deals with signing, encryption, and other things. But before I can dive into the HOSE specification, I'd like to go through the basics of hashing, signing, and encryption, and then we'll see how those translate to a JSON Object Signing and Encryption specification. So quickly introduce myself. My name is Sam Bellen. I'm a developer advocate engineer at Auth0. If you've never heard of us, that's perfectly okay. We're an identity as a service provider, which basically means that we try to make it as easy as possible for anybody to implement a secure authentication flow so you can focus on building your actual applications and you don't have to worry about logging in and registering users. We do that for you. I'm a Google developer expert, and you can find me on the internet as @SamBego. I'm also a JavaScript developer, so it only makes sense to me that I'm npm installable. So if you run npx @SamBego/about me, download Have the Internet and wait a few seconds, you'll find all the links to my social media and to these slides and other slides straight in your CLI or in your terminal. Cool. If you'd like to follow along on your own devices or see these slides again in the future, hose.sambego.tech. They will always be there. They might be updated in the future, but the gist of this presentation will always be available at hose.sambego.tech. And a little disclaimer, I might simplify certain things. Because we're dealing with cryptography, which can get quite complex quite fast, I might simplify certain things, so you will probably not be an expert, neither am I, but I will try to explain the basics in an easy and understandable way. Also, don't reinvent the wheel. Use the libraries that are out there that deal with anything cryptographic, just so you know they have been proven to work, they've been made by people who know what they're doing. Don't try to write your own if you don't know that much about cryptography. Also, the most difficult part about cryptography is pronouncing the word cryptography. You will hear me struggle a lot with that. So what we're going to be seeing, hashing and keyed hashing, signing, encryption, and lastly, the HOSE specification, JSON Object Signing and Encryption. So, hashing. What is hashing? A hashing algorithm is a mathematical algorithm that maps data of arbitrary size to a bit string of a fixed size, which basically means that no matter how big the input is, the output will always have the same size depending on which algorithm you use. So if you input one sentence, one word, one letter, or a whole book, the output of a hashing algorithm will always have the same size depending on the algorithm. And the initial data is often called the message, while the output of that hashing function is called the hash or the message digest. And it's a one-way function, which means that if you put something in that function and you get your hash back, you cannot reverse that hash back to the original input. It's a one-way function, input, hash, not the other way around. So if we look at a little example, we have 3 inputs. We have dog, doggo, and the quick brown fox jumps over the lazy dog. 3 different inputs with different sizes, but the output will always be the ssame size. In this case, it's a SHA-256 algorithm, so the output will always have a 256-bit length, and it's a one-way function. You cannot reverse the hash back to the original input. But it's good to know that if you input the same message, dog, you'll always get the same message digest, the same hash for this algorithm. So it's always predictable. You know which hash you're going to get from each input if you've done it once before. So some more used hashing algorithms are MD5 and SHA. If you've been on the internet a long time, you might have saved passwords in MD5. We don't use that anymore, but MD5 still is usable in some other use cases. Cool. that was hashing real quick. A variant of hashing is keyed hashing, which basically is everything we know about hashing, and it adds another thing on top of that, which is the integrity and authenticity can be validated with a key that is also part of the keyed hash. So in order to compute a keyed hash, you need a secret key, a password, so to say, something that is secret and only you know, so you can create those keyed hashes. So the same example, 3 inputs, a keyed hashing algorithm, and 3 outputs, but it doesn't only take that input, it also takes that secret key, that password, and depending on that secret key, the output hashes will change for the arbitrary inputs. So this means that you can validate the authenticity of a hash. If you know the key, you can add it to the algorithm and you can get the output that you expected. If somebody tries to recreate that hash, that keyed hash, with a different key, with a wrong secret key, they will get a different output, so they will not be able to get the expected hash that has been expected. And some of these algorithms are HMAX, SHA-256, 384, and so forth, where the number is basically just the bit length of the output. And like I said, these are not just random letters. They actually do mean something. It's keyed hash message authentication code for secure hash algorithms and a 256-bit output. Depending on the length of the output, that number will change. Cool. So some example use cases. When you store a password, you might store them as a hash. You might store them as a keyed hash. You might use something like DECRYPT, which goes even further. But in theory, usually we don't store passwords in plain text. We store them in some way of a hash in our databases. Just because it's a one-way function, should those hashes leak, nobody can get to the real passwords, and because it's predictable, as long as the user types in the same password over and over and over again, the hash we know and we stored in our database will also be the same over and over and over again. Cool. Hashing, keyed hashing. I'm going quite fast because we only have half an hour to go through all of it, but it's just the very basics of all of these cryptography thingies. Next up, signing. Digital signatures offer all properties of keyed hashing, so everything a keyed hash can do, a signature can also do, plus they offer something that's called cryptographic non-repudiation. Kudos for me for saying that correct for the first time. But if you look it up on Wikipedia, it says, non-repudiation refers to a situation where a statement's author cannot successfully dispute its authorship or the validity of an associated contract. Much clearer, right? To me, it just means cryptographic non-repudiation can prove who created the signature. Based on the signature, you can prove who created that. That's the same thing if you sign your signature on the bottom of a document, it's your signature, and in theory, it proves that you made that signature, even though we can obviously forge them. It's the same principle. That signature is linked to yourself, to your name, to your personality. So cryptographic non-repudiation enables other parties, other than the signer party, to check the signature's validity. This means that anybody can check if that signature is valid, not just you yourself. So digital signatures are usually use public key cryptography or asymmetric cryptography. It's very difficult to pronounce, which means that the signer creates the signature using their private key, and the person or the instance, the service that wants to validate that signature will check the validity of the signature using a public key. And that's something we need to remember if we go forward in this presentation. With signing, you use a private key, something that you keep private to yourself, to create a signature, and anybody can ask for your public key to validate those signatures that you have created. And usually a signing algorithm is not just one algorithm, but a few, something that creates a public and private key pair. They're always linked together, something that signs, something that creates a signature itself, and something that allows you to validate or verify those algorithms, those signatures. So if we look at another example, again, we have an input, we run it through the signature, the signing algorithm, in this case it's RSA, and we add our private key, because we use a private key to create a signature, we get a signature. If then in the next step we want to validate that signature, we just enter the same input together with that signature we created in the first step, run through the verification algorithm together with a public key, and then we'll get in either yes, it's a valid, or no, it's not a valid signature. And because that signature is based on the content, you can basically verify that the content is what you expect it to be, because the signature signs that content. So some of the more common algorithms are RSA, elliptic curve, and Edwards curve octet key pair, where RSA is the most common ones. You have a few of the algorithms that use RSA keys. RS and PS are the most commonly used, where the numbers, again, is the output length of the signature. And the good thing is, they're very fast to compute because they're quite simple in terms of cryptography. They're quite simple, which means that they're also CPU friendly because the mathematical algorithm underlying this algorithm is not that complex. And they have good support, especially RS-256 and the other bit lengths of this, because it's an algorithm that has been used on the internet and with programming in general for quite some time. But it also means that you need longer keys for a basic level of secureness, and a minimum of 20 56-bit is recommended, which also means that you get longer signatures. Well, if we look at elliptic curve keys, ES is the most commonly used algorithm that uses elliptic curve keys. They require shorter keys for the same amount of security that those longer RSA keys have, which means you have shorter signatures, but it also is a more complex algorithm, so it means that it's slower to verificate and it's slower to create those signatures. And lastly, address curve key octet keys. They're basically the best of both worlds. They offer the best signing performance, they're quite secure, but they're relatively new, so they might not have the best library support out there, even though today most libraries that deal with this kind of thing have support for address curve octet keys, which is a good thing. Some examples, JSON Web Tokens. I touched on it on the beginning of this, in the introduction of this presentation. I will touch on it again. Usually, JSON Web Tokens are signed. There's an asterisk there because you can also use them with keyed hashes instead of a signature, but the use case is the same. And document signing, or if you want to sign a message on the internet to make sure that nobody tries to tamper with it in transport, you can use signatures for that. So the last thing I want to touch on before we go to the real deal is encryption. I think we all have an idea of what encryption is, but when encrypting data, we can not only ensure the integrity and the authenticity, like with keyed hashes, but the data will stay secret for outsiders, which means that nobody else should be able to read or to get to the actual content of an encrypted message other than you and the person that it's intended to be received by. So you will either need a private key, a secret key, or a password, depending on the algorithm, to encrypt and decrypt those messages. And the encrypted message is called a cipher. When I say a cipher, it's the output of an encryption algorithm. So there's two kinds of encryption. You have symmetric and asymmetric encryption, where symmetric is a bit faster, a bit easier, because it just uses one key to both encrypt and decrypt. It uses a one secret, and it's very commonly used with systems that have to deal with big data, that have to encrypt big pieces of data, like your file system, like a database, like Wi-Fi protected access. Because it's simpler, because it only uses that one secret to encrypt and decrypt, it's more performant, and that's why we use it with these systems which deal with large data. And some of these are the ones listed here. You don't have to know them. It's just that there's a bunch of those algorithms out there. And if you look at how they work, again, you have an input, you run it through the encryption algorithm, and you get a cipher. And then that cipher you can send to the person or the instance that you wanted to receive, but it will not be readable by anybody else except the people that have access to that shared secret, which is used to both create the encrypted message and to decrypt the encrypted message. Well, if we look at asymmetric encryption, you don't use one key to both encrypt and decrypt. You use the receiver's public key to encrypt the message and use your own private key to decrypt. Where we used the private key to create a signature before and the public key to verify it, it's the other way around here. Here you ask for somebody's public key and you generate an encrypted message with the public key. So you yourself can use your own private key, which you keep private to yourself, to decrypt the message, and only you will be able to read that message using your private key. So if we look at the same example, you have an input, but we don't use a shared secret for both encryption and decryption. We use a public key to encrypt it, and we use a private key to decrypt it. Some examples are TLS, VPN, SSH. I think we've all heard those before. And some algorithms are RSA, OAP, and ECDHES. And it's good to know, I mentioned this before, symmetrical algorithms are faster than asymmetrical ones, just because the symmetrical ones just use one shared key to do both things, while with an asymmetrical ones you have a private key and a public key, and both of them have their own separate tasks. So let's look at a detailed example of how RSA actually work, because it's one thing to say, hey, you can generate public keys and private keys and use them to encrypt and decrypt data. Let's see how it works under the hood. So the first thing you need to do is generate that public key and that private key pair, which are mathematically linked to each other. And if note on cryptography, it usually uses very large prime numbers, and RSA is definitely not an exception. And when I say very large numbers, do I mean 1 million or 1 billion? nope, I mean something like this, where this would be a million and this would be a billion, and I have no idea how to pronounce the actual number here, but I think it has like 150 digits. So when we deal with cryptography and prime numbers, they're usually very, very big numbers, which makes it easy, it makes it harder to compute, but also makes it hard to crack those encryption algorithms or these encrypted messages and signatures. So what we do with RSA is we create two prime numbers. They're usually very large. In this instance, they're very small. It's 61 and 53. And we create a lambda, which is a lambda function based on those two prime numbers. We keep those in memory, but we will use those to both create the private key and the public key. And the public key will contain the modulus, which is the first prime number times the second, and the public exponent, which is the co-prime of that lambda. Well, the private key will contain that modulus again, the first prime number times the second one, but it will not contain the public exponent. It will contain a private exponent, which is a bit more complicated than just a co-prime. But this is the algorithm that runs RSA under the hood. You have to remember that there's two prime numbers and a lambda generated in memory, and you use that data to mathematically link the public key and the private key, so you can use them while encrypting and decrypting messages. So once we've done this, we can use a public key to encrypt. So if you have an input of 1, 2, 3, 4, I'm using numbers here because it's easier to explain mathematical algorithms with numbers. And you use the public key. You can do m to the e modulus of n, and the n is the public exponent, and the e is also found in the public key. And you get your encrypted message, for which for this input is 2183. Usually you deal with something else in numbers, so you have to do some data conversion. But under the hood, all of these algorithms still use mathematical functions, so they boil down to using numbers and mathematics. So if we remember that 2183, and we input it into the decryption algorithm of RSA, we take that message, put it through the decryption algorithm, which is written in the yellow box, and use the data which is available in our private key, or modulus again, and our private exponent. We will be able to get back to that initial 1, 2, 3, 4, because the public key and the private key are mathematically linked to those two prime numbers and that lambda that we generated in the beginning. So that's a basic gist of how RSA works under the hood. Under the hood, you create those two keys mathematically linked based on those prime numbers and some other arbitrary things you might generate from those prime numbers as well. And again, usually you don't deal with numbers, but you deal with some other data formats, so you have to do some data conversion. But under the hood, it's just mathematics. So I created a little CLI tool. If you're interested in it, I'll share the link to the GitHub in a few slides. But basically what you see here is the exact same thing. We create the prime numbers, the modulus, the lambda, and the private and public component. And you'll see that if we input 1616, we get a cipher of 1360, and the other way around. If we decrypt it again, you get back to 1616. But if we use real big numbers, real big prime numbers, these ones are like with 154 digits and more than 300 digits. That's when you get to the real way of doing encryption and decryption with RSA using very big prime numbers. So if you're interested in this demo, this is just for demo purposes. There's a link to my GitHub, which has a few branches that does all of this a bit more complicated, starting with small prime numbers and going to an example with data conversion. But it basically implements RSA in a few lines of code if you want to know more about how it actually works under the hood. Don't use this in production. So we've seen hashing, keyed hashing, signatures, and encryption. Just the basics, we know what they are, we know when we can use them. So it's time to dive into Jose. I still have 11 minutes, so I think that should be enough to talk about JSON object signing and encryption. And like I mentioned in my introduction, it's a standard that has several standards. That's basically a collection of several other standards. JSON Web Tokens is one of them, but there's a few others which I'd like to talk about now. So JSON object signing and encryption. Why JSON? Well, JSON format is often used for serializing and transmitting structured data over a network connection, which basically means that we use it on the internet all the time. We prefer it over XML because it's much more readable, much more user-friendly, and also it has excellent support in most programming languages. It even has native support in JavaScript, so that's really cool and really nice to work with. So JSON Web Tokens, there's a lot of JSON Web somethings in the Jose specification. And the first thing is a JSON Web Key, because it only makes sense that we can also share public keys with everybody. So it only makes sense that we can also share them in a JSON format. So if we look at an example of a JSON web key, you see a bunch of JSON. There's a bunch of properties in that JSON. It tells us which algorithm this public key is meant for. It tells us a lot of things, but it also tells us the public exponent and the modulus, which we saw when we created the keys in our RSA example, are the N and the E values in a public key. So all of that data is just available in a JSON structure with JSON web keys. Next up are JSON web signatures, which basically is a signature or a signed message in the form of JSON. And if you've seen JSON web tokens before, you might have seen something like this. A JSON web token always consists out of 3 parts. That's because a JSON web token usually, not always, but usually is a JSON web signature. Where the first part is going to be a header, a base64 encoded JSON object, which is the header. The second part is a base64 encoded JSON object, which is the payload. And the last part is the actual signature, which signs the payload and the header. So you know that nobody tried to tamper with the content in that header and in that payload. So if we look at the Jose header, the first part, it just tells us which algorithm that the signature is has been used to create the signature, so we know which algorithm to use to verify that signature. If we look inside of the payload, again, it's a base64 encoded JSON object. So if we decode that JSON object, it can contain anything that's valid JSON. It can be arrays, can be objects, can be numbers, booleans, strings, whatever it is, as long as it's valid JSON. And lastly, you have the signature, which basically means that you check in the header which algorithm has been used. In this case, it uses HMAC SHA-256, which is a keyed hash, but that's the only exception. It's usually a signing algorithm. And you pass along the header and the payload and the secret or the private key, depending on which algorithm you use, and you get the signature, which means if something changes in that payload or something changes in that header, that signature will also be changing. So that means that you can use that signature to validate the content of the payload and the header. Cool, JSON web signature. JSON web encryption is the last and most complex one that I'm going to be talking about for the Jose specification. But instead of consisting out of 3 parts, it consists out of 5 parts. Where the first one is familiar. It's our header. It's a base64 encoded JSON object that is our Jose header. The second one is, again, it's all base64 encoded JSON objects. It's our encryption key or encrypted key. The next one is the initialization vector, the cipher text, and the authentication tag. And the good thing to know is that the cipher text is the actual encrypted message here in this JSON web encrypted object. So JWEs not only use one kind of encryption, they use 2 kinds of encryption. They use symmetrical encryption and they use asymmetrical encryption, and they combine those for an even more secure effect. So how does this work? The content encryption key is usually encrypted with an asymmetrical algorithm, which means an algorithm that uses a private key to decrypt and a public key to encrypt. And you can use that content encryption key then later to decrypt the actual cipher, which is just a symmetrical algorithm, which means you can use that content encryption key to both encrypt and decrypt. So the first thing you need to do is decrypt that content, that JWE encrypted key. So how do you do that? You look into your Jose header, and it tells us which algorithms to use, and it tells us also which private key to use to decrypt the message. So the first thing we need to do is decrypt the content encryption key, the first step in decrypting a JSON web encryption object. We look into the header. We see that we need to use an RSA OAEP, in this case, algorithm, which is an asymmetrical algorithm. It also means that we need a private key. And it conveniently tells us that we need to use a key with the ID, ND, whatever. And if we pass along that private key together with the content encryption key, which is the second part of this string, into the right algorithm, we will get a decrypted content encryption key. Which means that we can use that key to decipher the actual encrypted message in this JSON web encryption object. So once we've got that key, we can pass it along. We can look into the header again, look for which algorithm to use. Once we find the algorithm, we can just take that algorithm, pass along the cipher, which is the encrypted message, together with the decrypted content encryption key, together with the initialization vector. How do you say this? Initialization, I cannot pronounce this. It's not something from Limburg, I guess. And the authentication tag, and if you paste along all of the moving parts, in the end, you'll end up with the decrypted message. So It's a bit complex, but you basically use an asymmetrical algorithm to encrypt the actual secret, the actual content encryption key, and once you've decrypted that, you can use that key to decrypt the actual message, which will use asymmetrical algorithm. And that's because this content encryption key is usually short, it's usually a small size, and this cipher might be a very big size. And we've seen in the previous slides that you can use asymmetrical algorithm for bigger pieces of data, while you can use asymmetrical algorithms for smaller pieces of data. Cool. So why is it called JSON object signing and encryption if it's just a string consisting out of 3 or 5 parts? Well, both JSON Web Signatures and JSON Web Encryption can be serialized as compact, which means these strings with 3 parts and dots in the middle, or 5 parts and the dots in the middle, or they can be serialized as JSON, where this would be a JSON Web Signature. It contains the exact same thing, the signature, the header, the protected things, the payload, it contains all of that, but in a JSON object. And this is a JSON Web Encryption object. So why would you use one or the other? This is more readable, this is more programming friendly, but if you have to send it with every request, for example, it might be easier to just serialize it as a string because it's much more compact and much smaller to send over the wire. Okay, JSON Web Tokens, I have to touch on it because I mentioned it a few times, but a JSON Web Token can be a JSON Web Signature or a JSON Web Encryption. And 99.99999% of the time when we talk about JSON Web Tokens, they will be a JSON Web Signature serialized as a compact string, meaning the 3 parts with the dots in the middle. But it can be any of the other forms as well. If you want to encrypt the content of the JSON Web Token, you can use in JWE format as well, which is much more difficult to parse. And most of the time it doesn't make sense, but if you want to be super secure, you can also use JWEs for JSON Web Tokens. So, the same thing, but instead of having just the algorithm and the header, you will also see that the type is a JSON Web Token, so we know that it's a token. So whenever we see this, we can deal with it as it being a token. And a token can be different things. An access token will give you access to an API, and will give you information about the API. So the payload of an access token will contain information that is useful to the API, things like the audience, which API it's intended for, things like the subject, which user this token has been issued to, and so forth. Well, if it's an ID token, it's something that's issued when you use OpenID Connect and you authenticate, so it will contain information about the identity of the person that has authenticated. So it will contain things like a nickname or name or a picture. So tokens can contain different content depending on the use case, but when you use a JSON Web Token, usually you have JWT type in the header as well. So I spoke a lot, I spoke very fast, I had a lot of things to say, so let's summarize this in a few short sentences. Hashing compresses and makes it virtually impossible to get to the real data. It's a one-way function, always has the same length of output, but you can never reverse a hash back to the original input. Keyed hashes protect the integrity of data, so everything a hash can do, a keyed hash can do as well, but it includes this secret key, this password as well, so you have to know the password, the secret key, before you can actually get the required output. Digital signatures allow third parties to verify the validity and origin of data. If you want to send something to some other party and they want to make sure that what they're receiving is the exact thing that you have sent, you can send along a signature which basically verifies that what they are receiving is or is not the thing that is intended for them to be received. Encryption allows only authorized people to read the data, only if you have the right public key, private key, or the right secret key, you would be able to decrypt the message, and anybody else who doesn't know those credentials would not be able to read the message. And HOSE is a set of standards based on JSON that helps us deal with signatures and encryption on the web. It helps us serialize them in a compact way so we can send them quite fast over the internet, or it helps us to serialize them in a JSON way so we can use them much more easily with our programming languages. If you want to see these slides again, jose.zambega.tech, but I'll tweet them later as well if you're interested in those. If you're interested in JSON Web Tokens, I maintain a website called jwt.io, which has a debugger and a lot of information and a huge list of libraries that help you deal with JSON Web Tokens in whichever language you write. JavaScript, most of us, I guess. And there's a few blog posts on our blog as well. That being said, thank you very much.